Okay, we can describe a black body, right? There's this plot here that I've put up here. We can describe the power emitted at any wavelength in terms of something called Planck's law. Planck's law states that the emissive power, E, which we call EB lambda. So EB lambda is the emissive power of a black body at a particular wavelength, EB lambda. That's going to be equal to this equation, which is C1 divided by lambda to the fifth, lambda to the fifth, times exponential of C2 over lambda times T minus 1. Okay. So this is our equation. So if you were to pick, let's say, a given temperature, some certain temperature, you could plug in that temperature there and plot out any one of these curves as a function of lambda. The C1's here, so I was just going to say, so this is really just a function. So this is just a function of lambda and temperature. Right, you pick a temperature, or you say you pick a wavelength, you could plot the same curve for all temperatures. But we need to know what these constants are. So C1 is actually 3.7428 times 10 to the 8th. The units on that are watts, micron, which is micrometer, the fourth, divided by meters squared. Right? So these are natural constants. These are constants that are just derived empirically from nature, observationally, let's say. C2 is what? 14,388 micrometers Kelvin. All right. So again, this is Planck's law. It describes the curve that we're showing here for the black body. One thing I want to point out though before we move on is there's kind of an interesting property of these black body curves. And a few things actually. One is that you can see pretty clearly as we increase in temperature, we're stepping up in temperature, the power emitted by the surface goes up, not just linearly with temperature or whatever, it's going up by orders of magnitude with temperature. And so you see here, right, look at the units here, this is a log scale. So down here, let's say here we are emitting. So our peak emitted power is going to be on the order of say 10 to the, 10, anywhere from 10 to 100 watts per meter squared micron. Like that's what we're emitting. If, however, we go up to the temperature of the sun, which is up here, we're now a full, 7 or 8 orders of magnitude, millions or tens of millions of times more power emitted per unit area for this same little square of area at that temperature. So it's a huge difference in radiation. The other thing that's interesting here is this blue line, right? So this blue line here, if we connect all the maximum power points on each of these, we find the wavelength where the power emitted is maximum as a function of temperature, plot that out on a log plot, it actually is a straight line, right? And that's a really interesting thing because it describes really concisely what temperature is, right? And this is given, or is called Wien's law. Right, so Wien's law says the following. It says lambda times temperature, right? So the lambda being the maximum, the wavelength of the maximum emitted power, times the temperature at that power is equal to a constant. Right? It's just straight equal to a constant all the time. So again, if you give me a temperature, I can tell you right away based on Wien's law at what wavelength it's emitting its maximum power. It's kind of an interesting thing. Last thing that's interesting here is this curve here. So this curve, the temperature of the sun, we put in here a box that shows where the visible wavelengths are. This here, this is visible. So it's no coincidence, I would say, that the visible region for us is in this region where the power emitted by the sun is the greatest, right? Our eyes have evolved to adapt to the fact that we get the most power from the sun in this region. So that's where naturally we want to see. Right? So just kind of some things that connect together here. Any questions on this? Okay. All right, last maybe kind of interesting thing for you physicists out there. So who knows what this is? Anybody know what this is? Yes. Cosmic microwave background radiation. So this is a map if you were to look out into the universe from our vantage point of what the temperature of the background radiation in the universe is. We mentioned, and why am I showing this other than I'm nerdy? So we're talking here about black body surfaces. In reality, there are no black bodies, right? There's nothing that really behaves exactly like a black body, with maybe a few exceptions. This is one exception. So this map here shows what looks like a lot of variation. But actually, what this is showing is temperature. And so this is the background temperature. There's something like, let's see, what is it? It's you guys probably know this off the top of your head. It's 2.725 degrees Kelvin. Plus or minus what? So plus or minus, and this is where the variations in the plot, it's 0.002 Kelvin. So a spike, that like red dot is say plus 0.002 Kelvin above 2.725. The dark blue is minus that. So it's this really uniform temperature distribution. But the reason why this is interesting is this radiation is not emitted by a surface. Right? It's not like this is stuff that was emitted from stars and has been bouncing around. This is stuff that's left over from the formation of the universe. And so it looks different from anything that we experience in our day-to-day thing, in our day-to-day interactions. And if you plot out, let's do this way. So if you plot out the spectrum, this is a black body curve, not on log, but just in standard coordinates. You plot the spectrum of the background radiation and compare that to a black body radiation, they exactly overlap. Right? So this shows that the background radiation that exists actually was not emitted from a surface. It's not, it doesn't behave the same way. It behaves like a black body. So there's reasons for this. We don't probably have time to go into it, but it's not especially relevant. But it's just kind of interesting that there are actual black bodies, but you have to go to really kind of extreme examples to get to it.